Hi students, today I am going to explain analysis of LCR circuit. Till now I completed pure resistive circuit, pure capacitive circuit, pure inductive circuit, and I completed CR circuit and LR circuit also. Now I am going to explain LCR, inductor, capacitor, resistance. These three components are connected to AC source. Now you take one resistor, one inductor, one capacitor in series combination. If they are connected to AC source of electromotive force ERMS. When electromotive force of any source is given, definitely it is RMS value. Peak value we need to find out. For example, in our house we are using 220 volts of electromotive force AC EMF. But whether it is peak value or RMS value or mean value, which is one? There is no doubt this is RMS value. When they are saying the 220 volts power supply is nothing but it is RMS value of this EMF. When I am connecting this AC source of particular electromotive force to this LCR circuit. LCR means what? R is the resistance of the resistor, L is the self-inductance of the inductor, and C is the capacitance of the capacitor. Now, here resistor opposes the electric current, inductor opposes the electric current, the capacitor also opposes the current. This opposition offered by the resistor to the electric current is called resistance. Inductance, the opposition offered by the inductor to the electric current is called inductive reactance. Which is denoted by XL. Then capacitor also opposes the opposition offered by the capacitor to the current is called capacitive reactance. The XL is nothing but omega L, which we already discussed. XC is nothing but 1 by omega C. Omega L, angular frequency into self-inductance. This product is called what? It is the opposition offered by the inductor to the electric current is called inductive reactance. The opposition offered by the capacitor to the electric current is called capacitive reactance, which is equal to 1 by omega C. Those symbols are XL and XC. So now we are going to discuss what will happen. Every time I am go on giving. For example, if you are taking the E equal to E naught sin omega t formula. Finally, what is the current relation? By using the EMF relation, we are finding the current relation. If it is pure resistive circuit, if the E is equal to E naught sin omega t, then I is equal to I naught sin omega t. So there is no phase difference. If it is pure inductor circuit, E is equal to E naught sin omega t we discussed. But what is the current relation we got? There is no doubt you got I is equal to I naught sin omega t minus pi by 2. That means what? It is current and electromotive force are out of phase with 90 degrees. Here current is behind the voltage by 90 degrees. Here current is behind means it is 90 degrees behind the voltage. In this way, if you take the combination of resistor, inductor and capacitor, there must be a current in the circuit now. This current, how it is related to the EMF, we are going to discuss that. Now, you know, when a current is passing, when a pure resistor is connected to the AC source, what will happen? The current and voltage both are in the same direction. That means current in the resistor, current flowing through the resistor and voltage across the resistor both are in the same direction. We already discussed. But when the same current, because the resistor, inductor, capacitor all are connected in series combination. When appliances are all components are connected in series combination, same current passes through all the appliances or all the components. So that's why current passing through the inductor is same I, but voltage across the inductor is VL, which we already discussed. That means voltage is ahead of current by 90 degrees. But in case of capacitor, the same current passes through it, but the voltage is VC. The voltage is behind the current. This things already you know it. But if you take this picture at a time, VC is in this direction, VL is in this direction, but VR is in this direction. VR is in the direction of the current. Only voltage across the resistor is in the direction of the current, but voltage across the inductor is perpendicular to the current, and voltage across the capacitor is also perpendicular, but only thing is opposite direction. Now our goal is to find out the impedance of the circuit. Impedance means effective resistance of the combination of these three. You know, for example, if VL is greater than VC, for example, voltage across the inductor is more than the voltage across the capacitor. If the two voltages are in opposite direction, then net voltage is what? Difference of these two. So that's why you can take this as VL minus VC. Then voltage across the resistor is same. Voltage across the resistor I am taking the same direction, but voltage across the inductor and capacitor combination I am taking VL minus VC. I am assuming that VL is greater than VC. If you consider VC is greater than VL, so you will get the figure like this. If the capacitor voltage across the capacitor is more, you will get like this. You can choose this or this to understand the topic. I am choosing this one. If the VL, this is the voltage across these two components. I am assuming these two components are acting as a single component. The voltage across this is VL minus VC. The voltage across this is this. Then effective voltage, actually potential difference, voltage, electromotive force, all these are scalars. But still we use like a vector addition. So VR, V, this is one potential difference, this is one potential difference. The effective voltage, the effective EMF or voltage both are same, but if you go deep there is a difference. So the net electromotive force in this circuit, the net electromotive force due to these three components is sum of these two, but it's not normal sum. You cannot say that this is VR plus VC plus VL. You should not take like this like a scalar. So you need to take like a vector addition. So that's why you can write E square is equal to VR square plus VL minus VC whole square. That means diagonal of a right angle triangle square is equal to sum of the squares of other two sides. It's like a Pythagoras theorem. E is nothing but electromotive force of the combination of this. So but you know the opposition offered by these, you know, V is equal to IR. V is also can be written as EMF. But in the place according to Ohm's law, E can be written as I into R, current into resistance. But in the place of resistance, we need to write impedance. I already said Z is the opposition offered by these three components to the electric current. Opposition offered by these three components is called impedance. Z is called what? Impedance. So impedance is measured in ohms because it is also similar to resistance. Resistor opposes the current. This combination of LCR also opposes the current. This opposition is called impedance. It is also measured in ohms. So that's why in the place of E, you can write I into Z. Here Z is acting like a R. So I square Z square. VR can be written as I square I into. VR means what? Voltage across the resistor. So you can write IR. Now, here voltage VL minus VC. This can be written, this voltage can be written as I square VL minus VC. You can write it as XL minus XC whole square. If you take the I common, finally you are getting Z is equal to R square plus XL minus XC whole square and square root I am bringing here. So therefore, the impedance of the circuit is this much. Impedance means opposition offered by these three components together. If you want to find out the current in the circuit, according to Ohm's law, V is equal to IR, you know it. It is also written as E is equal to IR. So I can be written as E by I, E by R. So here also, current in the circuit is nothing but EMF in the circuit divided by Z. So it can be written as E divided by under root R square plus XL square minus XL minus XC whole square. Therefore, you can write this equation in another way also. E divided by R square you write as it is. But XL is what? Inductive reactance, which is equal to omega L. This L is subscript, but this L is not subscript. Inductive reactance. This XC is nothing but omega C. This is already discussed in the pure capacitive circuit, whole square. But this is also having square. So Z is nothing but under root of this value. So the current in the circuit is electromotive force divided by impedance. Impedance Z is this. Now if you go for phasor diagram, here this is VR, this is VL minus VC, but the net electromotive force is E. This is here VL minus VC you can take here also, because it is acting like a vector. You can shift from here to here or here to here. So now the VR is the voltage across the resistor. VL minus VC is the net voltage across the inductor and capacitor. These are 90 degrees with each other, but the net electromotive force is the sum of these two, but it is not normal sum, it is like a vector sum. This is called phase angle. This is called what? Phase angle. What is the meaning of phase angle here? Phase angle, here I already said the current and voltage across the resistor are both are in the same direction. The net electromotive force given by the LCR circuit is making certain angle with the current. This is called phase angle. This is called what? Phase angle. So phase angle how can you find? Very simple. Tan phi is equal to, this is nothing but VL minus VC. Tan phi is nothing but VL minus VC divided by VR. But if you take VL in terms of current and resistor, current and resistance, finally you will get tan phi can be written as VL is what actually? Current into XL. VC means what? Voltage across the capacitor. I into XC. That means current into resistance. According to Ohm's law, V is equal to IR. So I into R. R is resistance, but here XL is resistance offered by inductor, which is called inductive reactance, divided by I into R. If you take the I common, finally you are getting tan phi can be written as XL minus XC divided by R. You can write by using if the voltage, when you are doing numericals, if the voltages are given, use this formula to find out the phase angle. If the inductive reactance, capacitive reactance and resistance are given, use this formula. This also can be written as tan phi. Sometimes they will give you XL is nothing but omega L, XC is 1 by omega C and R. So if the inductive reactance and capacitive reactance is not given directly, but they are giving angular frequency of the AC circuit, AC source, and inductive self-inductance of the inductor, capacitance of the capacitor. If these are given, use this formula. Depending on the situation, which formula is suitable to do the numericals, that is very, very important. First, you need to decide the formula which is suitable for the problem and do it. So, to find the phase angle is nothing but the direction of the net EMF. And E, this is the magnitude of the electromotive force, net electromotive force, and this is the direction. I hope you understood. Now if you now we are going to discuss about the special cases. You know already phase angle formula, tan phi is equal to XL minus XC divided by R. If in special cases, if XL is equal to XC, what happens? Then tan phi is equal to what? This XL minus XC both are same, so you will get 0 by R, so you are getting 0. That means tan phi is 0 means what? The phi is also 0. Because current, if the XL and XC both are same, but XL and XC, inductive capacitance, inductive reactance are opposite directions. That's why they get cancel each other. But even though resistor, inductor, capacitor, 3 are connected in series combination, if the inductive reactance and capacitive reactance both are equal, you can assume that it is a pure resistive circuit. This is also called resonance. In this case, it is called resonance. I am going to explain resonance in the next class, don't worry. Now, this particular case is also called resonance. So, here this situation, in special cases, this situation is called, in this situation you can call it as this circuit is a pure resistive circuit. Now if you go for second case, this is the first special case. In the second case, if XL is greater than XC, that means what? If the XL is greater than XC, you will get positive. So tan phi is equal to, so XL is greater than this, definitely you will get the positive value. That means this circuit is, in this circuit which is dominating? The inductive circuit. So, inductive reactance dominating circuit. Inductive reactance dominating circuit. This is a special case. But if you go for third one, if XC is greater than, this is XL, if the XC is greater than XL, then it is called, this circuit is called capacitive reactance dominating circuit. Here inductive reactance is dominating, here capacitive reactance is dominating. But here, if the resistance is dominating, it is called pure resistive circuit. This case is also called resonance. What is resonance? Everything I will explain in the next class. So, I hope you understood these cases.